Yes, the degree of excitation prior to the impulse transient does affect the susceptibility of the generator to pole slippage. Pole slipping occurs when the synchronous speed of the generator, which is determined by the frequency of the alternating current power system, falls below the actual mechanical speed of the generator. This can occur due to sudden load changes, faults, or other system disturbances. When pole slipping occurs, the field current in the rotor changes direction rapidly. This rapid change can induce large reverse voltages across the diodes in the generator, potentially exceeding their reverse voltage withstand capability. This in turn can lead to diode failures and subsequent damage to the generator. The degree of excitation, whether overexcitation or underexcitation, significantly affects the generator's ability to withstand pole slipping. When the generator is overexcited, the field current is stronger. This creates a more stable magnetic field, which helps maintain synchronism during disturbances. Consequently, overexcited generators are generally less susceptible to pole slipping. Conversely, when the generator is underexcited, the field current is weaker. This creates a less stable magnetic field, making the generator more prone to slip poles during disturbances. To mitigate the risk of diode failures due to pole slippage, several protective devices and operational safeguards can be employed. Firstly, diode snubbers can be installed. These devices are designed to absorb the reverse voltage transients across the diodes, effectively reducing the risk of diode failure. Secondly, overexcitation relays can be used. These relays continuously monitor the generator's excitation level and automatically increase the excitation in response to sudden load changes or other disturbances. By increasing excitation during these events, the likelihood of pole slipping is reduced. Thirdly, field suppressors can be implemented. These devices inject a current into the field windings to counteract the reverse voltage transients, thereby protecting the diodes from overvoltage stress. In summary, the degree of excitation prior to an impulse transient does indeed affect the susceptibility of a synchronous generator to pole slippage. Overexcited generators are less likely to experience pole slipping, while underexcited generators are more vulnerable. The implementation of protective devices such as diode snubbers, overexcitation relays, and field suppressors is crucial for minimizing the risk of diode failures resulting from pole slipping events. These devices enhance the generator's resilience to disturbances and ensure its reliable operation within the power system. Consider the scenario where a synchronous generator is operating within a power grid. Under normal operating conditions, the generator's electrical output is synchronized with the grid's frequency. This synchronization is maintained by the balance between the mechanical power input to the generator's rotor and the electrical power output from its stator windings. The generator's excitation system plays a critical role in regulating the voltage and reactive power output, ensuring that the generator operates within stable limits. Now let's imagine a sudden disturbance occurs on the power grid, such as a short circuit or a large load change. This disturbance causes a temporary imbalance between the mechanical power input and the electrical power output of the generator. As a result, the rotor begins to accelerate or decelerate relative to the synchronous speed of the grid. If the disturbance is severe enough, the rotor may slip a pole, meaning it rotates by one or more complete cycles relative to the rotating magnetic field in the stator. This pole slipping event can induce large transient voltages and currents in the generator's windings, particularly in the field winding and the associated excitation system. The diodes in the excitation system are especially vulnerable to these transients, as they are designed to conduct current in only one direction. When a reverse voltage exceeds the diode's reverse voltage withstand capability, it can lead to diode failure. The degree of excitation at the time of the disturbance significantly influences the severity of the pole slipping event and the magnitude of the resulting transients. An overexcited generator, with its stronger magnetic field, tends to be more stable and less prone to pole slipping. The stronger magnetic field provides a greater restoring force, which helps to keep the rotor synchronized with the grid. In contrast, an underexcited generator is more susceptible to pole slipping, as its weaker magnetic field offers less resistance to changes in rotor speed. To mitigate the risk of pole slipping and diode failure, various protective measures can be implemented. Firstly, fast-acting automatic voltage regulators, also known as AVR, are employed to maintain a stable voltage level during disturbances. The AVR adjusts the generator's excitation current to compensate for voltage fluctuations, thereby enhancing the generator's stability. Secondly, power system stabilizers, also known as PSS, are used to damp out oscillations in the power grid. The PSS modulate the generator's excitation to counteract oscillations and improve overall system stability. Thirdly, protective relays are installed to detect abnormal conditions, such as pole slipping, and initiate corrective actions. These relays can trip the generator offline to prevent further damage or instability. Additionally, diode snubbers can be used to protect the diodes from transient overvoltages. These snubbers consist of resistors and capacitors connected in parallel with the diodes, which help to absorb the transient energy and limit the voltage stress on the diodes. Moreover, field suppressors can be employed to quickly reduce the field current during a pole slipping event. By rapidly reducing the field current, the transient voltages and currents in the generator's windings can be minimized, thereby protecting the diodes from failure. The location of a synchronous generator within the power grid also influences its susceptibility to pole slipping. Generators located closer to the source of disturbances, such as large load centers or transmission lines, are generally more vulnerable to pole slipping. Therefore, careful planning and coordination are essential to ensure that generators are strategically located and adequately protected. In summary, the mechanism of synchronous generator pole slipping involves a complex interplay between the generator's mechanical and electrical characteristics, as well as the dynamics of the power grid. The degree of excitation plays a crucial role in determining the generator's susceptibility to pole slipping, and various protective devices and safeguards can be employed to mitigate the risk of diode failure. By understanding the underlying principles and implementing appropriate protective measures, power system operators can ensure the reliable and stable operation of synchronous generators and the overall power grid. Another aspect of synchronous generator operation to consider is the impact of prime mover control. The prime mover, such as a steam turbine or a gas turbine, provides the mechanical power input to the generator's rotor. The control system of the prime mover regulates the speed and power output of the generator, ensuring that it operates within stable limits. During a disturbance, the prime mover control system can play a crucial role in preventing pole slipping. If the rotor begins to decelerate due to a sudden load increase, the prime mover control system can increase the mechanical power input to the generator, thereby counteracting the deceleration and maintaining synchronism. Conversely, if the rotor begins to accelerate due to a sudden load decrease, the prime mover control system can decrease the mechanical power input, preventing the rotor from slipping a pole. The effectiveness of the prime mover control system depends on its response time and its ability to accurately track changes in rotor speed. Fast-acting prime mover control systems are essential for maintaining stability during severe disturbances. Furthermore, the generator's grounding system plays a critical role in protecting the equipment and personnel from fault currents. The grounding system provides a low impedance path for fault currents to flow back to the source, thereby tripping the protective devices and isolating the faulty equipment. Proper grounding is essential for preventing damage to the generator and ensuring the safety of personnel working near the equipment. There are several types of grounding systems commonly used for synchronous generators, including solid grounding, resistance grounding, and reactance grounding. Each type of grounding system has its own advantages and disadvantages, and the selection of the appropriate grounding system depends on the specific application and the system requirements. Solid grounding provides the lowest impedance path for fault currents, but it can also result in high fault currents that can damage equipment. Resistance grounding limits the fault current to a predetermined level, reducing the risk of equipment damage. Reactance grounding uses a reactor to limit the fault current and provide additional protection against transient overvoltages. In addition to the above-mentioned protective measures, regular maintenance and testing are essential for ensuring the reliable operation of synchronous generators. Maintenance activities include inspecting the generator's windings, cleaning the cooling system, and lubricating the bearings. Testing activities include performing insulation resistance tests, impedance tests, and voltage regulation tests. These tests help to identify potential problems early on before they can lead to equipment failure. Furthermore, continuous monitoring of the generator's operating parameters, such as voltage, current, power, and temperature, can provide valuable insights into the generator's health and performance. By analyzing the trends in these parameters, potential problems can be detected and addressed before they escalate into major issues. In conclusion, synchronous generator pole slipping is a complex phenomenon that can lead to diode failure and potential damage to the generator. The degree of excitation, the prime mover control system, the grounding system, and the protective devices all play crucial roles in preventing pole slipping and ensuring the reliable operation of synchronous generators. Regular maintenance, testing, and continuous monitoring are also essential for maintaining the generator's health and performance. By implementing these measures, power system operators can minimize the risk of pole slipping and ensure the stability of the power grid. The design and construction of the synchronous generator itself also contribute to its ability to withstand pole slipping. The rotor's mechanical strength and its ability to withstand thermal stresses are critical factors. The windings insulation must be robust enough to withstand high voltages and temperatures. The cooling system must be efficient enough to remove heat generated during operation. The materials used in the generator's construction must be carefully selected to ensure their durability and reliability. The generator's design must also consider the potential for harmonics and other non-sinusoidal currents. These currents can cause additional heating and stress in the generator's windings, which can increase the risk of failure. Filters and other mitigation techniques can be used to reduce the impact of harmonics. Furthermore, the generator's control system must be carefully tuned to ensure its stability and responsiveness. The control system must be able to quickly and accurately respond to changes in load and other disturbances. The control system must also be able to protect the generator from overload and other abnormal conditions. The settings of the protective relays must be carefully coordinated to ensure that they operate correctly and protect the generator from damage. In addition to the technical aspects of synchronous generator operation, it is also important to consider the human factors. Power system operators must be well trained and knowledgeable about the operation of synchronous generators. They must be able to recognize the signs of potential problems and take corrective actions. They must also be able to communicate effectively with other operators and maintenance personnel. Regular training and drills can help to ensure that operators are prepared to respond to emergencies. Finally, it is important to remember that synchronous generators are complex machines that require careful attention and maintenance. By understanding the underlying principles and implementing appropriate protective measures, power system operators can ensure the reliable and stable operation of synchronous generators and the overall power grid. One important aspect to add is the use of digital signal processing, also called DSP, in modern generator protection and control systems. DSP allows for more sophisticated algorithms to be implemented, leading to faster and more accurate detection of fault conditions, including pole slipping. Adaptive protection schemes, which adjust their settings based on real-time system conditions, are also becoming more prevalent. These schemes can improve the sensitivity and selectivity of protection, further reducing the risk of unnecessary tripping and equipment damage. Also, advancements in power electronics have led to the development of more efficient and reliable excitation systems. Static excitation systems, which use thyristors or other semiconductor devices to control the field current, are now widely used. These systems offer faster response times and greater control over the excitation voltage, improving the generator's stability and performance. Furthermore, the increasing use of renewable energy sources, such as solar and wind power, is changing the dynamics of power systems. Renewable energy sources are often intermittent and unpredictable, which can create challenges for grid stability. Synchronous generators play a crucial role in maintaining grid stability by providing inertia and frequency regulation. However, the integration of large amounts of renewable energy requires careful planning and coordination to ensure that the grid remains stable and reliable. Grid-forming inverters, which mimic the behavior of synchronous generators, are being developed to provide inertia and frequency regulation in systems with high penetration of renewable energy. These inverters can help to stabilize the grid and reduce the reliance on synchronous generators. In addition to the technical challenges, there are also economic and regulatory considerations that affect the operation of synchronous generators. The cost of fuel, the price of electricity, and the environmental regulations all influence the profitability of synchronous generators. Power system operators must balance the need for reliable power with the economic constraints and environmental concerns. In some regions, there are incentives for generators to operate in a more flexible manner, providing ancillary services such as frequency regulation and voltage support. These ancillary services can help to improve grid stability and increase the profitability of synchronous generators. Overall, the operation of synchronous generators is a complex and multifaceted topic that requires a deep understanding of engineering principles, economic factors, and regulatory policies. By staying abreast of the latest developments and best practices, power system operators can ensure the reliable and efficient operation of synchronous generators and the stability of the power grid.